All right, hi everyone, I'm Andrew, and I'm presenting paper number 6 called Remote Robust External Malware Detection Framework by Using Electromagnetic Signals. I got most of these slides from the main author from Georgia Tech University. So to start off, some background information. As we discussed in class, side channels are a useful way to gain information about a device without necessarily having direct access to it. So like power, temperature, time, and then in this paper they examine electromagnetic signals. So as we've discussed, side channels can leak information and you can learn secrets about a device. And in this paper, the authors focus on using side channels for a positive, in a beneficial purpose, specifically to monitor and profile a device. So using the electromagnetic signal from an embedded device, they can determine whether or not a device has been infected with malware, or an attack is going on. So advantages of using side channels for security and trust is that the device doesn't have any overhead if it's the monitoring device is separate from the device being monitored, and there won't be any changes in the performance of the device if the monitoring system is separate. So this is good for resource-constrained devices like embedded systems and IoT devices. And then, so the key in this paper is the fact that electromagnetic radiation depends on the switching activity on the device, so what specific code is running, and that changes the signal that's generated. It can be measured from a distance away, it's localized, and there's no overhead on the system. So to get into the key observations made in this paper is that most of the time spent in a program for these embedded systems is in loops, which is periodic behavior. So if we look at some time waveforms, being periodic in time makes it lead to spikes in the frequency domain, and these peaks can indicate which region of code is being run. And then the next observation is the fact that the clock frequency then modulates the frequency activity of the software that's running. So then you get an amplitude modulated waveform with the clock frequency or the clock signal as the carrier frequency, and the overall envelope of it being the software activity. So that can be used to. That's just what they observed, basically. Basically the clock frequency influences the signal. So then you get these.
Signal
I guess effectively, or the clock carries it. Or
it's the clock level which is being impacted, right? It's the amplitude modulation.
Oh yeah, I guess so.
EM waves are
Yeah.
generated because
of the clock.
And the amplitude of the clock is being
modulated. Yeah, that's correct.
Right?
Yeah. Right. And then basically the peaks in the frequency get sent around the clock frequency. So then that can be used to learn about the device. And then the exact process of doing this monitoring, they start by splitting or converting the electromagnetic signal into things called spectral samples, which involves taking a short time Fourier transform of the signal, which is just a Fourier transform at specific time intervals or shorter time intervals. And these are set to be 1 second or 1 millisecond intervals. And then to compare these samples of the signal, they need to use a distance metric, or some way to compare them, which considers noise and possible variations in the frequency. And the way that this is done is using this metric called CAPE, this clock adjusted energy and peaks, which uses a normalized frequency value based on the frequency of the clock in order to be robust against shifts in the clock frequency, which can cause false positives in their measurements. The other key feature of this is that they consider the non-clock energy first. So then by comparing that non-clock energy, the non-clock energy of two samples, if it's different enough, then the samples are considered different, so then they can stop there. But if it's similar enough, then they would use the new distance metric to compare the samples further. And this helps if there's lots of noise in two signals, because if there still is a lot of noise, the non-clock energy will be similar. between two.
So what
or-
exactly are these? Like what do they correspond to in the spectrum? Like what
What do
is
you mean?
F and what is S?
Oh, so F is the frequency of like a peak in a spectral sample, and then F clock is the
That's all. No
yeah,
clock
yeah.
frequency.
Yeah, and then they normalize it in order to be more robust against different situations. And then the way this is used is that the framework first gets a sample of, or like they train a model to see what normal behavior would be like.
No, so
And then-
given the spectrogram, what are they working on? Like I'm still having,
Oh.
I'm not relating that formula with the short time Fourier transform. What exactly is going on?
Wait,
Okay.
so
You said they are capturing 1 millisecond short time Fourier transform.
yeah, so
And
there's
you
like the little
presented that
spectral
equation.
samples.
What's the connection?
That's these are the frequencies of the peaks, I guess. I mean, they didn't present the exact details of how.
No, so
This is-
what,
I don't know.
What peaks are they looking at?
Oh,
you
of
got
the-
paper.
of this- yeah,
So
sure.
The thing is the following.
Okay.
You got the slides.
Yeah.
So you are presenting it. So hopefully you went
Yeah.
deeper than the slides, right? So the
Yeah.
question is that what frequencies are we talking about? And I mean the short time Fourier transform has lots and lots of.
It's the peaks,
right?
or the like the
Which-
highest peaks, basically.
No,
So
only
they
the highest peak.
yeah, they picked like a certain number of the highest peaks and then compare them,
Okay.
basically. And then yeah, so then for
So
the
they pick certain number of high
yeah,
peaks
they
from-
pick like n highest peaks and compare them to determine. So like in one sample they'll have like they get the highest peaks and to compare them. Yeah.
Does anyone is that anyone who reviewed this paper? So how many peaks are there?
We have mentioned it, so that is essentially a metric for clustering that they'll be doing.
Uh-huh.
So they are using that because they say that it is set, the frequency, the peaks are centered at clock frequency, so they want the change in the clock frequency to go away. Like
Okay, right. So that is what will happen. So that's just normalizing the frequency.
yeah, then
Right.
they take the peaks and also consider humps at that. So it's like essentially trying to capture the maximum power pattern in that spectrum and matching it with the others.
Yeah, so then in the training, they use this clustering technique to group the samples into clusters based on, and then the clusters correspond to regions of code. And then they don't need any knowledge of the software that is running or the number of clusters that they want to create. And then using a finite state machine, they can learn what valid transitions between regions of code would be to use it during the monitoring phase. So then in the monitoring phase, the system classifies each sample it gets into a cluster or into an unknown region. So then it's grouped into a cluster if enough of the peaks match the peaks of that cluster. And then if there are n consecutive unknown classifications, then it reports it as an anomaly. And this, they used n equals like between 3 and 5 for this, and that just depends on the noise characteristics. Another important consideration was interrupts, which are just seen as like short bursts of activity in the signal. And then the way they handled that, they said, is to train on get samples of performance when interrupts occur, so that it can cluster those as well to identify them as normal behavior instead of an anomaly. So then this is a image of the measurement setup with an antenna above the processor reading the signal, and they tested various hardware devices and different software running on these boards. So some of the devices used ranged from Arduinos to ones with OSs with different clock frequencies, and then for all these they were able to successfully detect a number of malware attacks. Some of the key
So what kind of test did they do? Like,
I have that on the next slide after this. But just some of the good things about this being robust is that it doesn't need to know the source code. It can work on lots of different hardware, and it's robust against noise. So for the specific attacks, the first one was hijacking the control flow of a syringe pump, like how much is being injected. And then another was for the firmware modification of it. So there's the temperature control of a soldering iron that was being tampered with, and then the final ones were shellcode invocations to perform DDoS and random ransomware attacks. And basically in all these cases, they were able to detect that there was an anomaly occurring and identify that well. So this is what one of the spectrograms looked like for the ransomware attacks. You can see how each region of code is kind of clearly defined, or I don't know if you can see it so well here, but yeah. But basically there's like kind of lines and the times going downwards. And then comparing this to the training model that they had, they were able to identify when malicious attack was occurring. And then this was just comparing their results to previous work they had done, which didn't use their new normalized frequency. So this one worked better and had a higher rate of true positives, like correctly identifying an attack, even when the distance was increased away from the board.
So do they require that every iteration of the software is similarly impacted in the sense that, like, I don't know, like, for example, the syringe pump stuff, okay, so maybe if there's some sort of a control loop, do they require that the malware affect every iteration, or could it be like it affects 1 in 1,000 instructions because that's when something interesting happens, or it sends a message out or something? Like, because in the latter, if it is only impacting some small fraction of the iterations, then you won't see a peak, right?
Yeah, but I think that's
So
they
what's
played
the
with.
reason behind their attack? Or like, what was the attack? Are they claiming that, like, I mean, for example, if I just change, I don't know, like the initialization code where I send out some identifying information, but then the loop is unaffected, then you will not see anything in the spectrum, right? So
Yeah.
So what are the assumptions behind the attack?
I think part of the thing too is they could change the number of number of consecutive anomalies that they detected, which helped like identify like quicker bursts of activity. So basically, like if they wanted to make to correctly identify an anomaly, sometimes they wanted to make sure that they saw it occur over a long enough period of time. So then they would have some, but then if they made it shorter, they could sometimes have false positives where they thought that something went wrong, but it wasn't really something that happened. That was one of the trade-offs they had there. I don't remember specifically to like one iteration if that would make a difference. But I guess on this just had a list of some of the like results that they had for the different attacks and devices that they used. So they had high rates of true positives and low rates of the false positives. And that's pretty much a summary of it without getting into it. It was
doing, like, I mean,
oh.
For example, what was attacked in case of syringe pump? What was the reason it attacked?
Oh, so I was controlling like the control of the syringe pump, like making it.
No, so what did the attacker do to the board? Like, what was the specific attack? Something was being triggered, and going back to the question, was it something which was triggering the loop, or was it like where was the attack? What were the
that
instructions?
one? It was. I don't remember the exact details of it, but I think the point of it was that it could like still identify it on one of the.
No, I'm sure it can identify it. For example, if I perturb a lot. On the other hand, if I just add one instruction, then it would be hard.
I don't think it was. It was more. It was like based on some existing, like known attacks that were able to be performed. I don't have the paper with me right now, but
Like, were these some standard attacks they picked from other papers?
yeah, they were like existing standard, like wasn't anything super specific, but I guess it was a code reuse attack, where they like called, so they were calling like parts of code when they weren't supposed to be. It was changing the order of the execution at some instances. So then that's a noticeable difference, whereas not being super specific to one part of the code. Any other questions?
I think just a general comment.
Sure.
If you are going to use slides from the authors, then it's very easy to fall into the trap that you're not going to read the paper actually. Because the slide becomes the text.
Sure.
Which is why it's very important, because some of the questions I'm asking, actually they are answered in the paper.
Yeah.
Since
Yeah,
you're
no.
using their slides as a crutch, you never went into the paper on your own that deeply. I think it's generally a bad idea to get the slides from the authors, because then you
I
won't
figured.
understand the
Okay,
paper.
sure. I wanted to just focus. I focused on looked at the implementation part more than the exact
but-
attacks that they carried out, because I
Yeah,
figured it
but
were.
Those are
Okay.
actually in their talk, because this person was a faculty candidate. He talked about
Oh.
those things.
Oh.
The reason he
Oh,
wrote
okay.
it is because he wrote the paper.
Yeah.
For you to do it, you got to read the paper first.
Okay.
That's
Yeah.
the point I'm trying to make,
Sure.
right? Because I allow slides to be obtained from the authors, but that's more to save trouble on graphics and
Yeah.
talks and all.
Yeah.
But don't treat it as that, okay, I can only look at the slides and they have all the information. They don't.
Sure.
Because
Yeah, definitely.
The authors have it in their brain because they wrote the paper, but you will need to. Okay, anyway, let's go on to the next one. Thank you. Okay, so next one. Sorry. And you have sent me the.
Okay, so hello everyone. Today I'm presenting the multi-user, multi-device aware access control system for smart homes. And in this paper, just to give you guys a brief introduction about how the system works, it's a smart home setup that actually, this is going to be the very first and a very novel system that actually provides conflict resolution when you have like multiple users with multiple access to multiple devices. And then through the traditional systems, we have had access control mechanisms which consider one unique trusted user. But the problem is in like multi-user environments, users have conflicting demands for the different devices in the room. So there should be some conflict resolution problems to happen and help the users define their own criteria for the system. So here the authors propose the Kratos system, which is a user interaction, which has like a user interaction module, a back-end server, and a policy manager. So as you can see here, we can have like a trusted user, but then we can have like different people demanding the same thing. But all of it previously was used to be accessed through a hub, but now they're having a more dynamic system, so then it can control multiple devices at the same time. So here we have the problems and the threats to the module. So we have the impulsive command execution. So it's kind of like any command that is given at like the authorized user is executed by the system without considering like the overall demand of the problem. So how do we prioritize the different like users, and what are their priorities, and who can set up what priority for the system? And then how can we monitor the devices so that like no central monitoring, if there is no central monitoring tool, then we cannot control a multi-user environment to actually adapt it to different users. Then we have in the normal smart home setups as what we have for Apple or Samsung smart home and for all other smart homes available. There's only one binary access, which is like 0 or 1. If you give access, it's like complete access and they take over the whole environment. Or it's just like you don't give access, so it's just like some minimal access. But if you have someone just coming over to visit home, or like if you have a guest and they prefer to come like at the midnight, but you have set up this policy to close the door lock at 10 p.m., then how can you resolve that conflict? So then the guest can actually get in at 12 p.m. but at 12 a.m. But then at the same time you don't give away all of the requirements, or you don't give them all of the access or all the rules, so then later on they can actually delete you from the system, or they can actually restrain some of the access of the main users from the whole system. And then in this proposed design solution, what is nice about it, and I think it defines a very good project, is that they have actually implemented in real world with the Samsung smart home device, and they have actually tested it out with the actual users, and I give you guys the exact numbers on like how the policy worked out. And it's great that they actually looked out for what is demanded from the user. So what do they really want to see in a smart home system? If they need like access control, need of like a policy negotiation, conflict resolution, and specify like the different restrictions. So for example, a parent can actually set up a rule for their child that they cannot access like the coffee machine, or like they can have only limited access to certain devices, and like who gets the priority in a system. So how, if you have someone to set up like the thermostat, then who defines what is the final value to be set for the whole home. And then after actually surveying different people, so we have the strength of the work. And for the strength of this work, I think what is also very good to see in this paper is that they're trying to go about 5 different threads, and how you can actually manage this priority between the different people and between different priorities. So like you have some people to be given to be like overprivileged if you give them just the access to like the whole system. And if you have like the privilege abuse, so like if they have access, then how can they like delete the system or not? And then privilege escalation, unauthorized access. So if like after a certain time you don't want your guest to have access to your system, how is that defined? And then the transitive privilege. So if you define a guest and then that guest gives unauthorized access to another user, then that's what you don't want to happen for your smart home system. And then here, through the 3 different systems that they're defining, the user can actually interface with the device. And this is the architecture of the device. So we have the user interface, and the users can actually interact with the smart home devices. And then it goes back to the backend module, and then it defines some policies based on the 5 tuple numbers that we have, like the different values, the different time, the priority of the users that you can have. So it's kind of like what is the time frame that you're giving to each of the users, and for what values are you defining for each of the devices. So for example, if you're setting up a coffee machine or like a thermostat, then what is the temperature range that you want to set up for this specific device? And then we have the policy execution and the policy management in case there is a conflict, and there are 3 different types of conflict to be handled, and then at the end it gets sent back to the back-end server and analyzed, and then a notification is sent back to the users, and like a condition is set. So in this system, if we have 2 users, for example, we have Alice and Bob to set up a thermostat. For example, one of them sets it up to 65 to 70, and then the other user wants it to be like from 70 to 80 degrees. And so this is defined as to be a hard conflict, which is like the users actually have 2 different demands. but the system needs to come to a conclusion about this demand. What the system does is to actually offer negotiation. So the first step is to average it out and be like, okay, so are you good with something around like 75 to 78 degrees? And if the users actually agree, so the system sets it up for that degree. But if they go ahead and like they cannot come into a resolution, then it actually sends a message to the higher priority person in the system to actually resolve this confliction. And through that communication, then they can actually resolve the conflict. The other conflict is the soft conflict, which is if they have overlapping demands. So like for example, Alice wants it to be 75 to 80, and then the other person wants it to be like from 78 to 85, and then so the system sets it to 78 to 80, and then they will be happy about it. And then the other one is the restrictive access, which is for the parental mode, or like the hierarchical mode, which is the higher priority person actually sets up the priority and sets the restriction for the next user. And then so if the other user, for example, wants to access the coffee machine, then the system knows that this is not required for this specific user. And through the actual calculation and the time resolution for this whole system, they have calculated that if there is a hard conflict and if it has to generate some notification for the main user, then that's the most time consuming like delay in the whole system. Other than that, it's not going to be like a very long process. And the longest delay that was achieved was for 30 commands or 30 conflicts in the system. So that's why that's like the most time-consuming system in this architecture. Other than that, they were able to actually handle 100% in all of the requirements. And so this is just kind of like a dynamic of how it's happening. And so on average, the latency was about like 289 milliseconds. And they were able to actually look for like the different thread models, and for that their success rate was about 100%. And so they were actually able to handle all of those threats that I just talked about. And so the other aspect of this one is like they actually tried it out with different users, although it was not the point of the paper to talk about like how is it like user friendly or it provides enough information for the users. Actually the users rated out this whole application and this whole system as a 5-star, and the lowest one for was for actually we needed like conflict resolution and all that, so they gave it around like 4. But the rest of like the user interface and all that, everyone was happy about. So I think I went a bit too fast, and then so with this system is the existing smart home system. They do not have like a fine-grained access control over the system for like the complex system and like the asymmetry in the system. But with this Kratos system, they are actually a novel multi-user, multi-device platform that is able to actually set up priorities for the access and assign like priorities and authorization for the different users. It was actually used for Samsung Smart Things platform and evaluated with 309 different policy sets. And like the highest success was achieved, as I showed you guys, with the values. But the shortcoming in this one is that they're assuming that the main users, those who actually install the system, are not going to be the threats to the system, which is a shortcoming about the system. If in case someone who is not supposed to be authorized for the system, what if they set it up for you? And so when they're assuming that the user himself is going to install the system, so they have the higher priority. But what if, for example, you order it from Amazon and someone comes and install it for you, and you don't want to give the access to that person? So that's something that they do not assume to be there. But other than that, they were able to actually assemble it such that if you have an Airbnb home and you decide to actually give it out to some other extra users, you can set up the priorities, so like you can actually restrict them in time that they're going to be in the system, and then so after that, security wise, you're not going to give it away to the extra users. Yeah, that was this. Yeah.
So questions, anyone? So I mean, I think besides thermostat and parental thing, what other things did they talk about? I mean,
They have just the thermostat. They have the coffee machine that they're working on, and
so
they
what
have
were the coffee machines?
the coffee machine is like if you can set up. They don't have a lot of like examples about it. It's just like parental control of it. But like setting up the like the temperature for it, can you turn it on or not? And then the door lock, if you can lock the door
So
or
giving
not.
different users different
Exactly.
permissions.
Yeah, and like different sensors, or like if you have the light bulbs, if you want to turn it on at night or like at a specific time, that's another.
And besides thermostat, there are any other example where you have this kind of averaging of choices happening? You know, like in thermostat, you have the temperature thing. Is there any other examples or something similar?
The only thing is for the light bulb or like for the door lock. So if you set up like a time, then it says like, okay, just give access to this specific user if they want to come during the midnight. Or like for the light bulb, if you have it like a specific time, it just like sets it up. If you want it like afternoon, so then it says, okay, let's associate it to a certain time. Yeah.
Comments, like, I mean, devices you encounter in a daily life where you think this, you know, I think
What if someone doesn't want to negotiate the temperature?
yeah, actually, how was the negotiation working? Like, I mean, I was just thinking, like, I mean, one person goes sets a thermostat, another person goes later on sets a thermostat. So
It's just
what exactly-
digitally through your
No,
application.
but how was the negotiation working?
The negotiation is like if the average they agree on is good, like they already
No, but
agree on.
Let's say person A in the family sets it now.
Mhm.
1 hour later, person B comes and sets it. So, how do you decide? Like, what do they say? How to decide anything? Averaging versus, you know, it's sufficient time has passed on some new person and do something.
It's like it looks at if you have if you still have access to the system. So if you still have access to the system and you have set it up for like the time being and you're still in the system, then it asks like the two users if they want to set it to something
So how
that they
does
agree on.
So thermostat knows that the other user is still in the house. or something like
They
that?
have like a timing for each person, yeah. So like they have it in the system. That's how they're connected to the main hub. So like the information is sent there, and then
Sounds like there was a study at USC a few years ago where what they were doing was to set temperature in buildings. People from their phones could say it's too hot or too cold.
Oh,
Okay, and
uh-huh.
then essentially more like a voting was happening, and based upon that they were kind of setting this rule. But it wasn't so much of an access control problem. In that case, it was more like setting a comfort value that keeps most people happy.
I think for this one it goes like along the same lines, but then if it goes into like they cannot make a decision, then a higher priority person like the household owner will resolve the problem by hard setting it. Yeah.
Some of these devices like the thermostat and stuff, you can just like go up to the device itself and actually do it. But in this scenario, I'm guessing you're only able to change the actions through
The application, yeah.
So does that mean is there a way to like disable someone just walking up to the thermostat?
Yeah, no, that's what I was. So I think in this case it's all through the app. Yeah.
Yeah.
I guess you could imagine that thermostat, if it had the ability to know who is the person who is requesting. It's a lot more complicated than what they're making it sound in the paper. It seems to be, right? I mean, so firstly, you could imagine that the thermostat because like Google's Nest stuff, right? I mean, it has all sorts of information about the individuals. It can say that person A is the one setting it, so that's another that can be done. But even then, you have this issue of like people who are setting these things at different points in time, like who should take the priority in that case. Is there some decay happening? I set it at 4 p.m. and if my wife does it at 8 p.m., is my choice still have any validity or should it be discarded, right? I mean, that it's not simply a notion of averaging, right? I mean, it has to take into account presence and stuff like that. I think the parental or the Airbnb examples are more believable in the sense that a higher authority sets a range and a lower authority basically can operate within that, right? I mean, so like maybe Airbnb out the room, and I want to make sure that they don't put the thermostat into settings which are too early and will set it to a limit on that. Or likewise, I don't know, like someone coming to your home to clean it, they can open the lock once, but during a certain time, and that's it. Along those lines, I can see policy. Thermostat is a lot more complicated because it's also about preferences. There are also issues about like women feel the same temperature, more
Right.
perceptual sort of coldness or discomfort, right?
Yeah.
All those issues also come into play. So, anyway,
That's
similar.
yeah. Thank you so much.
Thank you.
No problem.
Unfortunately, okay, got it. Okay, got it.
Hi, my name is Michael, and my paper I'll be reviewing today is Real-Time Analysis of Privacy Unaware IoT Applications. So just a quick overview of what I'm going to go over. I'm going to do the introduction of the topic, the research questions of the paper, the research process, the evaluation results, and its future direction. So to begin, today IoT devices are a part of a huge and growing market and enable human-computer interaction. These devices include smart thermometers, door locks, cameras, the Ring doorbell, and more. There exists IoT applications that allow users to interact with their products, and while it may make life more comfortable, many users are unaware of how their sensitive and private information are being handled by these IoT systems. So within this paper, over the 540 IoT market applications reviewed, 64% of these applications potentially leak sensitive information about the user. There exists some IoT security tools such as Saint and FlowFence, but these are limited in precision and what the user can be notified of, and its threat detection. This is just an example of the vulnerability within IoTs. As we talked about a few classes before, a lot of users don't change their default passwords on their IoT, so it opens up a major security flaw for adversaries to sneak into and gain access of whatever information these IoT devices are sending out. And this is just an example of the vulnerability within these everyday tools. The research questions of the paper are: what are the privacy concerns of IoT users? What functions are expected of privacy analysis tools? How can security alerts be filtered by user preferences? How effective is IoT Watch in detecting sensitive data leaks and potential privacy behaviors in IoT devices? And what is the runtime performance of IoT Watch in terms of latency and storage? So before this group started their research, they did a little privacy survey with about 123 participants, mainly undergraduate and graduate students. And they asked them about the familiarity with IoT devices and if they know about the privacy issues associated with IoT. Some of the questions they asked were: what information would you consider sensitive if used in an IoT app or device? And they would list out a bunch of scenarios where data was leaked, and if you didn't guess it already, most people are uncomfortable with their information being leaked out. So 65 participants were uncomfortable with the way in which IoT systems handle their information, and 89 participants wanted to be aware of how their information was being handled.
Were these computer science type students?
Yeah, I think they were students that the graduate students were TAing for or something, because they offered them extra credit if they did the survey. So the problem being tackled here is users are unaware of how their information is being handled. It's very sensitive. For example, in this scenario, there's a little function of how a smart door lock is working. The user thinks all the IoT application and device is doing is it locks the door and it lets the user know what the status of door lock is. What it's actually doing is there's a function called leak info that lets a third party hard-coded contact know that nobody's home. This is just an example of a potential issue that might arise within.
So this is not something they're pointing out about any specific particular law on the market which currently is doing it.
No, it's just an example. There are some malicious applications on IoT platforms that do have malicious apps. Yeah. So their proposal was something called IoT Watch. It's a runtime privacy analysis system, and it was developed for Samsung SmartThings since it's a large platform for device and IoT applications. It contains user preferences and labels. We'll get into that later. And 3 phases of the tool is instrumentation time, install time, and runtime. At instrumentation time, it adds extra logic to the source code of the IoT application itself. It gathers the original source code through this series of steps. It first gets an intermediate representation, and then extracts abstract syntax tree of the app and implements custom node visitors to build the interprocedural control flow graph. Basically, they copy the source code from the original IoT application. Then they throw in their own source code or their own bits of code to create the UI for the privacy application, and it defines the sync call. So whenever that is being flowed out of the application, it recognizes those points within the original application and marks them. And this is just an example of how the IoT Watch will add its own code. So this was the original code we saw earlier. IoT then adds its own set of code within the sync calls whenever a message is being sent out, and it tells the user something is happening. There's a potential privacy issue in this area. The next phase of the IoT Watch is the install phase. So after IoT Watch copies all the information and adds its own information to the original source code, it asks the user for preferences, and these are some of the preferences they let the user decide upon. They also ask for user information. So, for example, your contact information that you want that you only want the information to be shared with. And then using all that information, it creates a second app for you to download. So now after you download that second app, now you can use the IoT application with more privacy awareness. In runtime for the IoT Watch, it uses a classifier to label the IoT strings as different types, such as location, user behavior, device info, date time. If the user doesn't want as many notifications, it also helps minimize the latency overhead because you get less notifications. The classifier they used was AutoML2 by Google, and they used 380 of the 540 apps on SmartThings to create their text IoT classifier. So it's just a visual representation of their system. So they would copy the code here, source code here, and then they add their own code at instrumentation portion. Then they ask you what your preferences are and your user contact information, and then they generate a second app for you to download at install time. Once you install it, your IoT app works as usual, but whenever information is being sent out of your application, it matches your information that you put in with whatever other contact is the recipient of your IoT application. And depending on what the string is and also who the contact is, it'll let you know if there's a potential privacy issue or potential privacy leak. So after evaluating their model, their IoT string classifier was pretty accurate, 94.25%. It failed in situations where idioms were used.
Where is that running?
Oh, sorry?
Where is the classifier running?
Oh, the classifier runs over here. They connect it to a cloud, so then they'll feed the string to a cloud, and then it'll bring back classification for what the string is.
But their device talks only to the Samsung system, the Samsung processor. So how do they study? How is their code getting access to whatever the next?
Oh well, they copy the source code and then they create their own.
Okay.
Yeah, they create their own set of code. So This from here, everything else is they're set up. So I stated earlier, IoT string classifier was about 94.25% accurate. It failed in situations where there were idioms or at times there were Spanish words in the IoT systems, which the classifier couldn't recognize. There was about a 105 millisecond latency associated with the classifier and connecting to the IoT cloud, and 1 kilobyte storage overhead. This is an example of how accurate the IoT watch was able to detect potential security risks, and this is only with internet connection. So within this model, they looked at messaging and internet connection. Both of them were 100% in terms of finding malicious output. So the current strength of the model is that it allows users to understand how their information is being handled within the IoT apps, and it's relatively novel compared to the other security tools that I presented in the earlier slide. It allows users to decide what they want to be notified of, and it's dynamic privacy analysis at runtime. So it lets you know as your IoT device is running. Some weaknesses is that hard-coded privacy leaks could remain persistent. So they don't actually remove any hard-coded information within the original source code. They just add on to the original code. So let's say you want to be notified of messaging, but there's a messaging hard-coded contact information somewhere within the original code. It'll keep notifying you of that even though you're aware of it, but it won't really do anything about it. It just tells you what issues there are, but doesn't really fix any of them. And yeah.
So does it need to know the source code of every app?
Yeah.
I'm not quite sure what's happening.
Yeah, so it grabs the source code of every app first. So right here,
How does it get that?
it gets it from the Samsung Smart Things. It's able to access.
So the Samsung Smart Thing, the apps have the code also there?
Well, they
Or
they
do
can
they
get
do binary? Because
yeah
this is-
they can get the source code, and then they perform some abstract representation of it to get a similar representation of that original code, and then they add their own
Why would the app nefarious thing reveal its source code?
within the fairy.
Yeah, this is an app which is potentially doing privacy leakage.
Mhm.
So why would these apps publish the source code?
Why would these apps publish their source code?
Yeah. Why would an app which is behaving badly ever publish its source code?
Well,
You
I
know
don't.
what I'm saying, right?
Yeah. I see what you're saying.
So,
Yeah.
so the source code is for an app which is doing some
Yeah.
privacy behavior, right? I mean, so why would such an app generally publish the source code?
Well, I think most IoT users don't really even check the source code in the first place.
But most IoT apps don't even publish the source code, so
Well, I think they didn't copy and paste the source code necessarily. They just kind of got an extracted version of it. They grabbed the functionality of the source code. They used. I didn't really understand too much about how they grabbed it, but they said they used an IR representation of the original code to get a layout of it, and then they used ASI and ICRP to further strengthen their. Yeah.
I think adding on to that, I think one of the requirements for having an app in whatever marketplace it could use is that the developers have to probably publish it.
is that so?
Oh, they do.
And you can extract the source code from Android apps.
These are not Android apps, so Samsung system, the apps are all running in the cloud and they're written using Haskell or some some weird language.
Oh, it was like Googly or yeah, it was a weird one.
Yeah.
It was Jubilee or something.
I mean, it could be that maybe they kind of.
Mhm. So yeah, hard-coded security risks won't get removed. And the future direction of this application is that since a lot of IoT applications are they're kind of primitive in terms of security checks, this provides a nice way for users to understand how their information is being handled by their home devices, such as Alexa or something. And then it can be further improved to troubleshoot those hard-coded instances, or maybe it seems like they only take a few user-defined contacts, so maybe if they broaden that as well. And it can also be implemented in many systems, but maybe they could also change something such that you don't have to download the app again. Maybe put some kind of second app that monitors their other IoT instead of having to reinstall every individual application.
And one thing I imagine that the platform itself, so in this case, in case of Samsung, all the communication takes place through their backend services, in the sense that if an app ever talks to another app, or if the app talks to the outside world, it will all being done at the portion of the app running on Samsung's cloud.
Mhm.
So Samsung as a service could monitor
Implement
that and
this,
can
yeah.
inform and say that, look, this app contacted all these servers, for example, right?
Yeah.
I mean, so, or it's equivalent to saying that what if Google or Apple were to provide us with all the information about where all an app was sending information to, for example. So like you might be surprised where
Yeah.
all, and then and maybe give you an option of blocking it or
Yeah.
this or that.
Yeah,
I mean, like right now, all we get to know is that app needs network, but we don't get to know that is it sending to a server which belongs to the company which the app is from, or maybe it is sending
Yeah.
to some weird place, right? I mean,
Yeah, so it's not too specific in that regard either. It just kind of lists them as potential risks and then lets the user know. And any questions? Yeah.
Just to be sure, IoT watches for the end user, right?
Sorry, could you say it one more time?
IoT watches for the end user, not the app.
Yeah, it's for the end user. They get the application, they put in their preferences, and they install an instrumented app with the IoT watch.
So I had tried to download it. There's another weird thing out here, which is they basically want you to sign and send data to them. So while in principle you could go ahead and run it locally and all, they don't kind of make it easy. So that's another challenge with some of these kind of services that now you are centralizing trust in one entity and you get to make sure. There's one case which was Facebook a few years ago started its own VPN service, and kind of the idea of the way they sold it was that this is more secure and all. But what Facebook was doing was that now they have access to every app that you were using because it was coming to Facebook, and they were scavenging the app and obviously advertising it more. EU has sued them over it, and this is when a company like Facebook is doing the work. You could say that they were misrepresenting. So I mean these kind of services. So what I didn't like about these guys was that the default thing was you were basically more signing up and data clearing agreement and saying okay, follow this. I felt that that's not how it comes in good. Their default should have been you can run it, data entirely under your control, and then by the way, you're also a research that you let us use as constantly. But otherwise, it's a nice piece of software if you can just modify it, step there, rapid code,
Any other questions? All right.
Thank you.
Thank you.
Alrighty, hi. So my name's Airlise, and I'll be talking to you today about the Plunderbolt software-based fault injection attacks against the Intel SGX. So just a little bit about what we'll be discussing. We'll be talking about the just general idea, what is Plunderbolt, what is it about, and what are the contributions that they made, the attacker model, assumptions that they made, and further details into how they actually developed the attack. Applications of the attack, so it's got a general concept to it, but it was able to access and fault into different situations, so we're going to talk about those. And then again, it attacked the Intel SGX. So this research and experiment that was done was actually so accurate and was able to be implemented in a real world setting that they were able to disclose this research to Intel, and Intel actually had to make an update. So we'll talk a little bit about what that was. So again, introduction to Plundervolt. Plunder means to rob, the violent and dishonest acquisition of property. So again, we're going to be talking about taking voltage away from the system. So in industry, like most of you know, power and heat consumption is a general concern. We want to make sure we're reducing power consumption, and along with that heat, we don't want things to get too hot. So different types of companies have created systems to optimize frequency and voltage through different control systems. Different companies do it different ways. Intel's way includes, their most recent processors include a separate voltage-related chip that the CPU controls, but we'll get into the details of that a little bit later. And then again, Plundervolt focuses on the Intel SGX memory encryption system. So other research has focused on other different parts of it. Other research has also done kind of similar stuff, but this is the one that's really been able to use voltage control to affect a memory encryption system, which hadn't been done before. Again, the SGX system is a general instruction set that increases the security of application code and data. So it's a security measure that was already added into an Intel processor, and they're still able to hack into that, basically. So a little bit about what Plundervolt does. So it's a software-based attack, but it has hardware results, right? We're affecting the voltage, but they're using software to do so. They attack the Intel SGX system, and they're controlling the operation through voltage. Because of this, they're effectively able to compromise the security of the Intel SGX and be able to extract information and other things like that. And again, they were able to disclose that information to Intel, which was really important for them. So the attacker model. A couple assumptions were made here. So for the attacker, they're assuming they have full access to the software. That includes remote access as well. So they don't need to be in the same room as the computer that's running this or any really physical connection to it. As long as they have full access to the software, the attacker is presumed to be able to follow through with the attack. Again, we're talking about Intel Core processors. So there is a limit to which ones they can apply this type of method to. It includes processors that go from the Skylake processor forward. So that's around processors from 2015 forward. And again, a little bit into the way this is calculated and everything. The voltage uses an 8-bit VID that comes from the CPU. And that's sent to the voltage chip, and that determines the voltage offset. So that VID is kind of related to this other set of code called the MSR. So this is an image with the MSR kind of line of code, or bits, sorry. That's a 64-bit code that really it contains two main aspects. So that contains the voltage plane and then the voltage offset. So again, the voltage offset is what's going to affect that VID and control the voltage. And then the plane is just kind of another part of bits that's related to the CPU. So one of the things that the researchers did find is that amongst all of the processors that they were looking at, it didn't really matter what the voltage plane was. They were pretty much all on the voltage plane. So whenever they did make an effect to the voltage, there's multiple cores. So if they changed something for one core, it would actually affect all 4 cores, for example. And then again, so their method uses undervolting. So because of this voltage offset, they're actually lowering the voltage. If they were to increase it, which they did try, this would result in just system crashes, and also just protections are already in place by Intel to protect it from going beyond a certain voltage limit, so there's not much they can do there. So their method is to undervolt and to lower the voltage. So what they were actually able to do is undervolt to a certain extent. So if they start to lower the voltage little, they would do it incrementally. So if they lower the voltage little by little, at first it doesn't really create an effect. And then the good range is that they actually create an effect and fault it correctly. And then if they go beyond outside of the range, it just causes the system to crash, which isn't really what the effect that they're looking for. And again, they also considered older models of processors. These don't really run SGX like the way the other ones do, so that kind of limits, again, the processors that they were using for this. So applications. So one of the main things and ideas that they used was for the multiplications. So there's different parts in the system that use different types of arithmetic, but multiplication was found to be the best one for this. Other things like addition and subtraction didn't really work out. But the multiplication, possibly because the critical path is longer, that it was actually able to work out. So that's one of the notes that they make. So this is a very simple example of what they used. I don't know why they used a hexadecimal deadbeat, but again, this is an example of a very basic example of what they actually were able to implement with the fault. So this while loop over here would pretty much run infinitely. Because of this multiplication that's going on, and then it's checking for that multiplication, and it's always going to be satisfied. Now, what they were able to do is create a fault in the system right after it does this multiplication. So it actually flips one of the bits of the value var. So when it checks again for the while loop and it checks var, it's no longer satisfied, and it jumps to this line, and you get the XOR. So that's something that they were able to show, that they were able to fault it correctly one, and then it flipped the bit and outputted the XOR of those two values. So this general idea is what they used to apply to the rest of the other applications that they used. Some of the ideas that they got from multiplying and doing these analyses is the more iterations that they were able to do, they were able to find that they were able to undervolt at lower values. And then undervolting to different types of CPUs varied. So different CPUs, even if they were this.
Way for it to change the blue background.
Let's see.
PowerPoint, right? So
Yeah. Yeah, we could turn off. I can do that. I think this is all the
yeah, it's probably all the right spots, right? Okay, that works. Yeah. Okay.
So again, one of the things that they found is that they looked at multiple CPUs, and some of them are similar models, but they have different model numbers. So they looked at those, and even within those, they have different base voltages, and they realized a connection between base voltage and the voltage that it took to get to lower to actually create a fault. So those were the differences that they found. Another thing that they also found was that temperature affected it. So they could have the same processor running, but it would require a different level of undervolting depending on the temperature of the room. But for the rest of the experiments, that was just an observation that they did, but for the rest of the experiments, they always kept it at room temperature. So that wasn't something that they considered into the rest of it. So moving forward, they also worked on key extraction. So they were successfully able to inject faults into complex cryptographic computations. This includes signatures and also RSA CRT key operations. So in their research they based it off of some research that was already done by the Belcore and Lenstra fault injection attacks. These attacks, they basically were able to inject fault again, and then from their research they were able to reset the voltage on these RSA modulus calculations. So from that, from executing those two things and then using the Belcore and Lenstra method, they were able to extract the RSA keys. So that's again another method of encryption that they were actually able to get into without having to physically code or do anything like that. They were able to extract it from these voltage faults. And then one other key information here for this one is that once they were able to get that key information, that really just can reveal all types of information. So it reveals information about the processor's long-term key material that should never be exposed to software. And another application was memory safety. So the compilers rely on multiplication results for pointers and memory allocation sizes. So most of the time we don't really think about these things, but it does use multiplication for that. So again, like our first example, it's able to fault into multiplication values and flip bits, and actually pretty consistently once they were able to do that research. So again, when they're accessing an array element, it multiplies to I forget the two values, but it multiplies two values again, and it actually will either find the wrong array element or something like that to do that. Other memory-related things were faulting into the IML instructions and finding other areas where multiplication could be targeted. They were also able to attack different types of arrays. Or also another example was this figure where they show that they can affect a launch enclave where erroneous multiplication bit flips allowed to be redirected as a trust. So that information in step 4 is actually, because of the bit flips and the way that they hack into it and they fault, it can actually be sent to a different type of memory page that the attacker can set up. So the attacker can set this page up, fault into it, and through their steps get the memory that they were looking for and have it sent to them. And then other more simple things too is like the size of function also uses multiplication, so they can hack and do that. So when you capture this size of function, instead of getting the correct size of it, it'll actually come out to be smaller because of the fault multiplication. And response from Intel. So they were able to responsibly disclose this information to Intel. This is their general response, but again, it included 2 things, mainly the BIOS patch to disable the overclocking mailbox interface configuration. So that really just indicates the MSR 150 that I showed before, that 64-bit line of bits. So that's what they're really indicating by mailbox, and they were able to patch this. This is actually one of the methods that the researchers were able to suggest. So they actually, at the end, suggest a series of countermeasures, and this is pretty much along the lines of what they suggested to do so. And then that's which leads me to the second part. They released some microcode update that will be released for the mailbox. Again, this is along their suggestion. So their suggestion directly was applying microcode updates that completely disable the software voltage scaling interface exposed via MSR. This isn't a perfect method. It doesn't cover everything because it doesn't cover the root cause of Plundervolt. But it's still something that would pretty much effectively make it a safer way to use and continue to use the Intel SGX. Besides that, there's still some other things that are exposed via hardware that they could be tapped into if someone was there physically, but this patch generally did the trick for them. And that's all. Any questions?
So questions, anyone? So I think this kind of work is representing kind of architectural, micro-architectural attacks being taken to get another level, and so I'm sure we're going to see more and more of these efforts coming out. Essentially, a whole can of worms, and I think, as you can see, Intel has to take it seriously because these are all very persistent attacks. So I think kind of the whole thing that the group which published this is one of the groups which are also co-discovered maritime, I think. But what is it? On the spectrum, one of the two. So they huh? Okay. Yeah. So I mean, they've been pretty active in a whole range of attacks. Anyway, let's move on to the next one. Last one for today.
Okay. Hello everyone. So today I'm going to present this paper on something known as butterfly attack, adversarial manipulation of temporal properties of cyber-physical systems. So this is more or less the contents. So we're going to give a background on the temporal weaknesses in cyber-physical systems. We're going to give the system model that the authors use in the paper. Then we're going to give the threat model of the butterfly attack and a brief description. And the authors applied the attack in 2 cases, firstly on electric vehicles and secondly on UAVs. And lastly, we're also going to discuss some of the mitigation techniques, and from my side, I'm going to present the strengths and weaknesses of the paper. So cyber physical systems are pretty much embedded in our everyday life, starting with smart home systems in our homes to electric vehicles and whatnot. And all of these systems are integrated architectures. Like a particular cyber physical system might have several other cyber physical systems. For example, the electronic control unit within a car might also be responsible for controlling maybe the GPS system of the car. So basically the notion here is, in order to save cost, the manufacturers tend to run multiple of these integrated systems and tasks on a shared platform. However, the weakness of this is that it opens up a large attack surface for the adversaries. For example, a particular adversary might jam a GPS signal, and in a way this might compromise the entire system. So with cyber physical systems and the concept of scheduling comes the physical notion of time. And basically the authors here have shown that this opens up a whole new class of attacks, what they call temporal attacks. So basically you can upset the stability of a control system by just manipulating the temporal properties of the system. So the exploit that they're talking about is that by increasing the jitter of a critical task, they can modify and how they do it, they just modify the execution time of a non-critical tasks. They can upset the entire system, and we can look how they do it. So here's the scenario. So we have like a shared uniprocessor platform, like we have a single processor controlling all of the tasks, and we assume that the tasks are periodic, real-time, preemptible, and independent, and all of them have specific deadlines. And the scheduling algorithm that the authors use is fixed priority preemptive scheduling or rate monotonic scheduling. And here's some other symbols as well, like the authors have also assumed that these tasks have criticality execution time period, and they've also assigned priority to the tasks. We should note that the priority and criticality are not the same. A high priority task might have a lower criticality and vice versa. And for the control systems, they're assuming that the control systems are governed by the differential equation as shown. So basically xi and ui, these are the planned state and the control signals respectively. For example, in case of a motor, this might be the rotational velocity or the voltage applied to the motor. And a and b depend upon the system dynamics and the physics. And we also assume that like if there are sensors, then the sampling is done periodically and the control signal is updated with some delay. So if we assume that the controller is a linear quadratic Gaussian controller, then the stability of the controller for a particular plant is given by the standard quadratic cost, which is the equation that's shown above. And here Q is a positive semi-definite matrix, and what Q basically does is it basically tells you like how to weigh the input signals and the control signals, like what will their effects be in the final standard quadratic control cost. And if the value of the quadratic control cost is infinite, then this denotes that the system is unstable. Now, how do we like combine the notion of stability with the notion of time? So basically what the authors have shown is that, like, suppose that this is like a task with a certain worst case response time and a certain best case response time. So they define latency as the difference of this, and jitter is defined as the difference of the worst case response time and best case response time.
So
And
latency is the best case time.
yeah, latency is the best case time, and jitter is the worst case minus best case response time. So they use something known as the jitter margin toolbox, and like if we assume that the stability conditions are linear and we're using like this is our process, then this is the equation for the stability condition. So there's some constant alpha and there's some constant beta, like if we plot latency and jitter. So this is the plot of latency and jitter, as you can see. Like as you have seen from the equation, like it's like a normal linear equation, and that's exactly what you can see in the graph. And if we from rate monotonic scheduling formula, if we substitute the worst case response time and best case response time into the equation that I've just seen, then overall this is the stability condition that includes the temporal properties of our physical system. So as I was saying, for the threat model, we said that we're going to upset the system by modifying the temporal properties of our non-critical tasks. So what are the assumptions? So we assume that the adversaries in no way cannot affect the temporal properties of the critical tasks. They can only upset the critical properties. We can only upset the temporal properties of the non-critical tasks, and they can only do that by modifying the inputs. For example, suppose that your non-critical process might be like your vehicle positioning system. So how do you modify the inputs? You simply jam the GPS signals, or you can like delay or advance the incoming signals as well. So our primary goal is to destabilize the plant by indirect manipulation of temporal properties of a critical task via the non-critical task. So here comes the butterfly attack. So the butterfly attack renders a task unstable by manipulating the time delayed experiences, and this happens because of the interdependent and non-monotonic properties of the cyber physical systems. By interdependency, as I've already said, that multiple tasks run on this shared platform, and changing the parameters of one task might change the parameter of other tasks as well. And by non-monotonicity, what I mean that if you like increase the processor time for one task, then this may increase the jitter that the task experiences, and in turn this might render the entire control system unstable.
But only if that task is a lower priority task.
Yeah, that's true.
Okay.
Yes.
So the idea here is the control task is a lower priority task.
Yeah,
even though
it's a lower priority, but it's of higher criticality.
Right.
Yeah. So they applied this attack to like two applications. So first application is electric vehicles. So the plant model is very similar. As I've shown earlier, here X is the rotational speed and armature current of the rotor, and U is the armature voltage, and A and B depends on the motor physics. So they assumed some values of A and B, and they came up with this equation of stability. And for tasks T1, they assumed like some predefined priority and computation time as well as period. And the goal of the attack here was to increase the period of the non-critical tasks. Here the non-critical task was the vehicle positioning system. And here's what happened. So basically at time t equal to 1 second, they increase the speed of the rotor, and at the same time the attacker jammed the GPS signal. So as you can see, like when we increase the speed of the rotor, the rotor speed starts like a bit sharp, like it's not stable, but it soon reaches stability. However, if the attacker upsets the system, then as you can see that the rotor speed never converges to the desired speed. And we can also see this more clearly from the control cost. Like once we increase the speed at time t equal to 1 second, the control cost does become stable here. But in the bottom curve, we can see that the control cost starts to diverge, and it never becomes stable. Very similarly, they also performed this attack on the UAV. So in the UAV, the non-critical task was updating the GPS signal, which means that you are just receiving GPS signal and sending it to the UAV's control unit. And the critical task was the motor control system here as well. So similar phenomena were observed. And apart from this, what they also did is that how do we like modify the position of the UAV apart from just upsetting the UAV system. So here what they did, they increased and decreased the period of the GPS between true value and a particular adversarial value. And by doing this, what they observed is they are able to modify the trajectory of the UAV. So the blue line that you see, like this is the normal path that the UAV should take. However, after the attack, as you can see, the UAV deviated from the path and it went through an unsafe area. So what are the mitigation techniques? So the authors did propose a lot of the mitigation techniques, and they also like mentioned the weaknesses of the mitigation techniques. Like the most obvious mitigation technique is like to execute a dummy task to compensate for the altered execution time. However, this would lead to poor resource utilization, like we are not using all of the processor time for the system applications. We could initiate a switch to a more robust controller if we detect this attack. However, like there have been papers that have like proved that switching to controllers might destabilize the control plane. We can also like promote low priority tasks and assign priorities with respect to task criticality. However, this might lead to deadline clashes, and this only applies to fixed priority scheduling. We could use a single robust controller. However, this may be more complex and resource intensive, and we might not be able to get the desired control quality as well. And lastly, what we could do is that we could use temporal isolation using processor bandwidth. That is, like we could assign a certain processor time to a certain task. However, like this might leave the processor clock underutilized as well. So what are the strengths and weaknesses of the paper? So the strengths is in the way that the attack is mounted. So the adversary does not need to like modify any of the system parameters directly. Like he doesn't need to interfere with the platform, the scheduler, or the execution of any of these tasks. And like even if the tasks are like protected, like even if all of the bus and everything is protected, the adversary can still mount the attack because you are basically messing with the inputs of the system. And the adversary is basically exploiting the counterintuitive and the innate interdependent and monotonic nature of cyber physical systems, like the way that cyber physical systems task scheduling works. And like there's no straightforward mitigation technique. Like we cannot say that a particular mitigation technique is going to work. As I've shown, like all of the mitigation techniques have some weaknesses. So what are the weaknesses of the paper? Like the results that they've shown are entirely simulated results, and they have not given the details as to how an attacker might mount all of this, GPS jamming and all of these attacks. Like at what time the attacker needs to mount the attack, and like what sort of devices the attacker needs to mount the attack. They have not given any sort of details on that. So what are the future work? So we need to evaluate the extent of this attack in real world scenario using real-time physical plans, because there are lots of other things that go on in these plans. And plus they assume that the controllers are ideal. However, there might be non-ideal controllers as well. So we want to evaluate data characteristics on that. And the primary future work is how do we devise optimal mitigation technique against these attacks? Like how do we protect the non-critical tasks in the first place? Like how do we prevent like messing with the inputs in the first place? Yeah, thank you.
Great, thanks. Any comments?
Yeah.
When I was reading the paper, I was confused on the extent of how much they can control, for example, the UAV.
Yeah.
Because in the paper they just mentioned they sent a particular adversarial
Yeah.
jamming signal.
Yeah, no.
And they never mentioned like what they used.
Yeah, no, that's like the exact thing that I said. Like they have not given the details as to how an attacker might mount the attack. Like,
So
like
do you think that you would be able to, for example, control UAV using this method, or is it more of an interference?
I think it's more of a
I think it's the interference.
I
Yeah.
think this work, you're absolutely right that, think of it more like giving an idea, but they have not fully developed the idea. But, so the takeaway for me was that jitter can cause potential issues with control algorithm, and jitter is something you can affect even if you are you can affect the jitter of tasks indirectly by other tasks that you need to do. I think we are seeing this issue of sharing in different forms is always going to create some issue in the period will be maintained that what kinds of games you can play with the control loop if you have control over the jitter is I think an interesting question for some control like to do also. There are, I guess, in these real-time schedulers, there are other effects also that we can imagine doing. Like, for example, I was thinking that these real-time schedulers, even if it was the highest priority task, it is going to be impacted by interrupts. So if somehow you have control over interrupt traffic into a system, then even if the control task was the highest priority task, it was going to consider it was a little bit like the denial of service type of attack, everything. So there's too much traffic and then you're impacting. I think it kind of opened this. I'm thinking of it more as a food for thought, but in practice I would use probably the cleanest answer is like everything which is time critical, better than it in a isolated practice.
I was wondering, if we switch to a hard real-time system, every task is timed, will we still have
These are
this?
hard. The scheduler they are using is what is used in hard real-time systems.
True.
Yeah. I mean, because the definition of hard real-time systems that people have largely used in the scheduling literature focuses on guaranteeing a rate and not guaranteeing lack of jitter. Okay, so the whole model in hard real-time, I mean, if you go to like textbooks and conferences and all, they kind of start out with this model that that being hard real-time to them means that they are able to sustain a rate, and that for every sample a deadline is met, not any guarantees in the second order probability definitely. So what this is, if these guys are right and that you can do damage by the jitter, then that questions speculation. and the only way you can control, make sure that the jitter is, unaffected is by being the highest priority task, of course, right? But even on processors, as I was pointing out, even the highest priority task is impacted by interrupts because they are even higher priority. Yeah. So the issue, the question here is the following: what all damage you can do by manipulating the jitter in a control loop? That's really.
Yeah.
If no other questions, so one other reminder: next Tuesday is the mid checkpoint for your project. So I don't know if I've already sent out the template or not, but probably not. But it's a let's see, so how many projects we have? We have 25 students in class. I'm assuming we probably have 10 or so projects. So I think last year when I done this course, we took for like 7 minutes or so presentation. That's not really expected. It's basically a forcing function on you are smiling, so what? You have something? Okay, good. Okay. So I'm going to send out the template and I'll just submit it via Dropbox. For that. Okay. So we're going to wrap up. Yeah. So I can, if any of you want to meet me, I can be in my office right now, so you can talk to the gate, and then I'll be there until 10 minutes before the hour, and then I'll again be for the breakup, the little office hours from 5:45 to 6:15. So, particularly for projects, if you have any issue, also if anyone needs to purchase anything still and you need for any hardware and all, you have to send it to me quickly. So